DeMoivre's theorem is going to feel similar to the multiplying of the complex numbers. Just like any other power rule or exponent type deal, you are going to do the same kinds of things you would do with multiplying. But you're doing multiplying over and over again. So it's important, if we're going to do this, to have our complex number in polar form. So we're going to do that first. And then we're going to do the same kinds of things as multiplying, but instead of multiplying now, we're going to raise our R value to the exponent that's on the outside, and we're going to multiply the angles by that exponent instead of just adding. So it's like we're adding over and over and over again. So first step here, we're going to change the polar form. Kind of putting together what was done in the previous two videos or in class. So in this case we have r is equal to square root of 1 squared plus the square root of 3 squared. And that's going to give us an r value of 2. Our tangent is going to equal 3 over negative 1. Now remember, you want to get the correct quadrant. So if we're looking at the point negative 1 is 3, we are working with quadrant 2. So the Q2 angle here is going to be 2 pi over 3. So our polar form is going to be 2 times cosine 2 pi over 3 plus I sine 2 pi over 3. Okay, once we have it converted, we're going to do the 2 steps to completing it. So we're going to change the, raise R to 12, and we're going to multiply the angles by 12. And then simplify. So again, it really reminds you of those exponent rules. When we raise an exponent to an exponent, we raise the numbers to that exponent and we multiply the angles. The same idea. So if we're going to do this to the 12th, we'll do 2 to the 12th times cosine of 12 times 2 pi over 3 plus I sine of 12 times 2 pi over 3. Now the simplifying, a lot of times we'll end up getting a number answer out of this. We get cosine of 8 pi, which we can get an exact value for, and I sine of 8 pi. You'll notice the angles will always come out the same. You're just doing sine and cosine of those angles. So it's going to be 4096 times 1 plus 0, and we end up getting a final answer of 4096. I'm just going to do one more example in a different quadrant just to kind of get the idea of what's happening and how this can be used. Okay, so this one we are working with negative 1 minus I. Again, when we're thinking about it and we're converting, it's like the point negative 1, 1, which is in quadrant, or negative 1, which is in quadrant 3. So we'll do R equals the square root of 1 squared plus 1 squared, which is the square root of 2. Nice thing is we're going to be raising that to the 4th later on, so it won't be a radical anymore. Tangent theta is going to be negative 1 over negative 1. So although it's a positive 1, we want to get our theta value to be in quadrant 3. That would be 5 pi over 4. Okay, so our complex form of this for z is going to be square root 2 cosine 5 pi over 4 plus I sine 5 pi over 4. We'll do z to the 4th. So again, we're raising the r value to the 4th, and we're multiplying the angles times 4. So this will come out to 4 cosine 5 pi plus I sine 5 pi. So we'll get negative 1 plus 0, which will give us a negative 4. So these won't always come out perfectly like this. If they come out to something that's a decimal, you can round it. But a lot of times you will be able to work with exact values in this type of situation.